All right, let's get right into it. We all think of Bitcoin as this fortress, secured by some seriously complex crypto. But what if the biggest threats weren't these massive brute force attacks? What if they were these tiny, subtle flaws just hiding in plain sight? Well, today, we're going to pull back the curtain on two of these hidden dangers that could have been absolutely catastrophic, and the really ingenious fixes that keep the whole network safe today.
I mean, that sounds completely backward, right? The one thing you do to prove you own your Bitcoin, signing a transaction, could actually be the very thing that gives away your keys. It's a terrifying thought, but for a while there, it was a totally real risk. Let's dig into how that could even be possible.
So this first vulnerability, it's buried deep inside the digital signature process itself. The problem wasn't with the strength of the cryptography, not at all. It was all about this one tiny secret component, a piece of data that was never, ever supposed to be used more than once.
And that secret ingredient? It's called a nonce, or more specifically, the K value. Just think of it like a secret, one-time use password that helps create your signature. Its only job, its one purpose in life, is to be totally random and completely unique for every single transaction you sign. The security of your private key literally hangs on that one rule.
And here's the shocking part. The way it fails is brutally simple. If a wallet's random number generator just messes up, even just one time, and reuses the exact same K value to sign two different transactions, that's it. Game over. Your private key is toast. Anyone on the planet can take those two signatures and, with some straightforward math, figure out your private key.
And let's be really clear here. This isn't some small information leak we're talking about. It is total, catastrophic exposure. A single mistake, one reused key, and the key that protects all your funds is just out there for anyone to see and, of course, to use.
And don't think for a second, this is just theoretical. This has actually happened. Real people have lost their Bitcoin because of faulty wallet software with badly implemented random number generators. It was a real active threat that cost people serious money.
So how in the world do you fix a problem that's rooted in something as wild and unpredictable as randomness? Well, you do something kind of brilliant. You get rid of the unpredictability. The solution was to stop relying on pure chance and instead build a system that was predictable, repeatable, and because of that, totally safe.
This solution really required a whole new way of thinking. The old way, it just relied on pure randomness, which created this single massive point of failure. If your random number generator had a bad day, your security was gone. But the new deterministic method, it's way smarter. It actually uses the transaction data itself plus your private key to create the nonce. And since every transaction is unique, this guarantees you get a unique nonce every single time. It completely removes chance and all that risk from the equation.
And this clever fix, it isn't just a suggestion. It's now the gold standard, baked right into the core rules of Bitcoin. Technical standards, like RFC 69079 and BIP 340, they're what ensure that modern wallets don't just leave your security up to a roll of the dice. They systematically prevent this single deadliest mistake.
Okay, so we've slammed the door on that vulnerability. Individual keys are much safer now. But what if an attacker's goal wasn't just to steal from one person? What if they wanted to attack the entire Bitcoin network at once? Well, this second vulnerability we're looking at allowed for just that, by turning a single, cleverly made transaction into a weapon.
It was called the quadratic hashing vulnerability. And here's what that means in simple terms. For the old-style Bitcoin transactions, the more inputs or signatures a transaction had, the more work a computer had to do to verify it. But here's the kicker. It wasn't a nice, straight line. The work didn't just double if you doubled the inputs. No, it grew exponentially. It got out of control fast.
So, of course, an attacker could exploit this. They could build this monster transaction with a huge number of inputs. And by doing that, they could force every single node on the Bitcoin network to perform an insane amount of calculations just for this one transaction. It's a classic denial of service attack designed to grind the whole network to a halt.
And the danger here really was exponential. A transaction with, say, 10 inputs, that's totally normal. But with this flaw, a transaction with 100 inputs didn't create 10 times the work. It created this massive, totally disproportionate overload that could bog down the entire system. So the fix for this massive, network-level threat came with a huge Bitcoin upgrade that you probably heard of, segregated witness, or SegWit.
Now, it's famous for a lot of things, but one of its most critical and kinda unsung contributions was neutralizing this exact attack.
What's so brilliant about this fix is that SegWit just fundamentally changed the math. It wasn't a patch, it was a redesign. It introduced a totally new, much more efficient way for nodes to calculate the hash they need for verification, completely replacing the part of the process that was vulnerable. And I mean, the difference is just night and day. Under the old system, the work grew quadratically, which created that massive overload risk. But with SegWit's new algorithm, the work grows linearly. So now 100 inputs is simply 10 times the work of 10 inputs. It's predictable, it's manageable, and it completely diffuses the attack.
The result was a massive win for Bitcoin security. This fix made verification way more efficient for everybody. It eliminated a major threat to the network, and it ultimately made the entire decentralized system that much more robust and resilient against attacks.
So what are the big takeaways from these two stories? Well, first is that the tiniest, most subtle bugs can have the absolute biggest consequences. Second, the really great solutions, they don't just patch a hole. They redesign the whole process to eliminate the problem from the start. And finally, it really shows that securing a network like Bitcoin is never just done. It's this constant, ongoing evolution of finding threats and building smarter, stronger systems.
And all of this leaves you with a really fascinating question to think about. We've fixed these two huge issues, but the work never stops. So what other subtle hidden dangers are cryptographers and developers out there defending us against right now, making sure the systems we're all going to be using tomorrow are safe?